the parameterization of the curve, we need only one parameter. Normally we call it t. Sometimes we call another letter theta, something. In this case, we need two parameters because the vector value function can generate two parameters of surface is the object in two dimensions. Not necessarily flat. Maybe in general is curvy, but it's a vector value function that contains two parameters. In general, we call U and B. But no, not necessarily U and B because normally I adapt the name of the variable according to the geometry idea for the surface, no? It doesn't matter. I like in the piece of paper I call different name. However, in GeoGebra I call U and B because in GeoGebra is a little bit hard using Greek letter. It's okay. So now we're discussing now three different surface okay, you know very well. However, I want parametrization, no? Because I want to use it in the future. For example, this. Suppose this example. Example is example 4 because in the last example we studied 3 examples. Example 4 is suppose x squared plus y squared equal 4, no? What kind of surface it is? What kind? What kind of surface it is?
A circle?
No, surface. Circle is a... Huh? Okay, the answer circle is wrong because circle is no surface. Guys, you are advanced students. You are a student that take multivariable calculus and you need to differentiate in your mind what is a curve, one dimension, and what is surface, two dimension, right? So my question was, repeat it, try again. Not necessarily you, another student. X squared plus y squared equal 4. And the two-dimension plane, I know, I 100% agree with you, it's a circle. But in three-dimension context, what is that? In three-dimension context, in three-dimension environment, what is that? Help me, guys, please.
A cylinder?
Exactly, a circular cylinder, a circular cylinder. Okay, a circular cylinder. By the way, what is the radius?
2.
2. Excellent. This is the idea. Okay, excellent. So you put in GeoGebra like that, no in parametric. You see a cylinder que continue forever, upward and downward. It's infinity. Okay, infinity cylinder. However, in parameterization, no. Parameterization is, suppose I want to declare, to understand this surface, one vector value function, okay, depending of two parameters. In this case, I want to call, because I want h and theta. Who is theta? Well, theta is the angle, ¿no? Que es the full cylinder. Entonces es, the component x es 2 cosine theta, comma, 2 sine theta. Okay, so far, si I close this, entonces now you understand que es a curve, no? And we declare another parameter I want to call h, or whatever you want to call h, que es the height. And you define, for example, que theta, very, from 0 to pi. And h, very, for example, is the portion of the cylinder you want to see from 0 to 10. Do you understand this idea? So we see no infinity cylinder. No. We see one portion of the cylinder que is starting n0, c, h is like c to 10. So that distance is 10. Make sense? So in the language of the GeoGebra, you using the function surface. Inside the surface, we have different expression, no? The first expression is, for example, 2 cosine theta. Pero suppose que in GeoGebra I never using Greek letter. Cosine u, comma, 2 sine u, comma, comma b, que es h, comma u, que es the name of the parameter, comma 0, comma 2 pi. This is this. Comma b, comma 0, comma 10. Okay, when you are doing this in GeoGebra, you see elegant, super elegant cylinder, circular cylinder along the z-axis, and of course the height is 10. Makes sense? Very, very important for me. Very, very important for me. You are doing now here a domain, que es theta and h is the new variable in the vector value function. And you can see how the domain is rectangular region. This is 0 to pi, and this is 0 to 10. Okay, and we have here, I put the different line to indicate the variation. This is the domain and the new plane, que es el plane h theta, no? So somehow, using the magic of the vector value function, you convert this surface, curve B, in the regular 3-dimensional space and 2-dimensional space, but no xy, h theta, and we can using this to compute the new integral that we studied. Okay, because this new integral that we study, finally we convert to the double integral in the region R. Yes, this region. Okay, any questions so far? Maybe you have some doubts, some think you, pero it's clear, right? Or no? No? Confusing. And this is, remember, this is parametrization. And this in my language is good parametrization. Why good? Because the domain is a rectangle and they're super easy perform double integral. Okay.
By the way, Professor, why is H10?
H is one variable que ahí declaré. Suppose Teo, ¿no? Es Teo. Es Teo. Who are you, Mr. Teo?
It's me, David.
David, okay. David, look. Suppose que you don't feel good with the H and you call Z. Because actually it's the distance around the Z. Entonces, this, you change that. It's a completely arbitrary name. The name is not important in this game. Okay, the name is not important. Pero define the, like the height or the portion of cylinder that you want to define. Good? Cool?
Okay, cool.
Okay. Let's continue. Let's continue. A little bit. This is a process, guys. This is complicated. Therefore, little by little. So basically, the thing that we studied so far is a new way, completely new, you never see before in your life, to define surface using parametrization. Example 5. Example 5. You help me, guys. Suppose this, x squared 999 x squared plus 4y squared plus c squared equal 36. What is that? What kind of surface it is? You put it directly here in GeoGebra. What kind of surface you see? What kind? Nobody know? Nobody know? What is the characteristic of the identification? And there are no missing variable, x, y, and z is present. in my equation. Everything is a square. Everything is positive. It's obvious. What is that? No? Nobody? Wow. And totally disappointing. It's a classic. Come on, guy, help me. Use your common sense. You pay attention. Ellipsoid, very well. Very well, very well, Álvaro. Álvaro say, es ellipsoid, professor. Okay, perfect. Es ellipsoid? Yes. Ellipsoid. Es ellipsoid. Ellipsoid look like the football ball, ¿no? Ajá, entonces suppose que I want to express en estándar. Standard right hand side is 1, ¿no? Entonces you divide by 36, everything. Ajá, entonces 36 divided by 9 is 4. And you can write like that, x over 2 squared. Make sense, right? Plus 36 divided by 4 is 9. And you express like that, y over 3 squared. Plus, in this case, z over 6 square equal 1. Everyone follow me in the algebra?
Yes,
Okay, now I'm using my famous spherical coordinate because sound good, because it's not a sphere, but it's similar to a sphere, ¿no? Ajá, entonces I declare que, for example, x, o sea, this guy, x over 2 is equals, and the formula for a sphere is 2 sine phi cosine theta. In a spherical, remember we have two, actually we have three, no? Rho, phi, and theta. But rho is constant. I suppose que es 2 in this direction, at least in the direction of the x. Okay, and y is 3 sine phi sine theta. It's the classical equation for the spherical coordinate. And z is 6 cosine phi. Therefore, suppose que, look, to show you this idea quickly, suppose que these two I move, divided to the left is x over 2, but actually this guy is sine square phi cosine square theta. Do you see this idea? So I try to this look like similar, no, to this. So you divide by 2, so you have x over 2 is sine and cosine. No? Likewise, y over 3 is sine, of course, square, no? Entonces sine square phi cosine, no sine, sorry, sine square theta, plus, this is cosine square. The cosine square phi. Y I suppose que should be 1. Should be 1. Okay, for example, I can see here que sine square is common factor. You factor out. Okay, no problem. And inside the parentheses, we have cosine square plus sine square plus cosine square. And this is 1. It's obvious, right? It's the famous trigonometry. And since 1, entonces sine phi plus cosine phi is 1. Boom! I proved this. Easy. Entonces we're using this equation for doing the parameterization and the vector value function of this surface, que is r as a function, in this case, phi and theta. It's our parameter, que has physical meaning, o sea, geometric meaning, ¿no? Es the component of the x, que es 2 sine phi cosine theta, comma, the component of the y, que es 3 sine phi sine theta, comma, and the component for the sec is 6 cosine phi. And that's it? No, because I need the specification, the domain of phi and the domain of theta. Okay, the domain of phi, let me try to do graphically to visualize much better. Suppose que this is theta, and suppose que this is phi. Angle, both are angles. 0 to pi, because I want full ellipsoid, and 0 to pi. This is our domain of, this is our domain of the vector value function. And in GeoGebra, for example, you write like that: surface. We practice this in the review package. We practice in another example. Surface command. You copy this expression. I copy 2 sine b, for example. I call phi like a b and theta like a u. Cosine u, comma 3 times sine b, sine u. Wait. This is multiplication, no comma. It's a period, time, multiplication. Okay, time. There, let me write properly. Is sine u, comma 6 times cosine b. Now remember, we need more information. We need to define who is u. U is the variable guy. In the paper I call theta, but in the GeoGebra I call u. I put from 0 to pi, and be a phi from 0 to 1 pi. And when you are doing this, bang, and you graph this, I want to show you in a few seconds. You see the famous ellipsoid. Any question? Any question? Any question? Do you follow me? Do you understand? Confusing? Complicated? Clear, guy, or no?
Yes, it's clear.
Okay. One more example, and that's it. One more example, and that's it. Okay, it's example 6. In the example 6, we have another surface. But this surface is defined like a x squared plus y squared less than or equal 1, and y plus c equal to. So basically, I don't understand very well what the hell is that. However, I try to do my best to understand this. The three-dimensional space, surface. We are talking about surface, no solid surface, flat, dimension 2. Entonces es obvio que this equation x squared plus y squared equal 1, suppose que I ignore for a moment the symbol less than, it's a cylinder, right? Cylinder of the radius 1, along the z-axis, no problema, and extending forever in both directions. However, we have a plane. This is the plane. The plane is y plus c equal 2, and that plane, x is missing, therefore this plane is parallel and travel along the x-axis. Therefore, if you find the intersect to understand this, you suppose, for example, y0, c is 2. So we get the point here. This point was 1, remember, no? Now 2 here. This is the point 0, 2, 0, no? Belong to this. And we have another case 2 here. 1, 2. is the point 0, 0,2. Okay, you are doing the line to understand a little bit the plane. No good, this line. You are doing the line to understand a little bit the plane. And this plane is extending, of course, in any direction. Extending. This is my plane, and therefore the idea is the intersection that plane with the cylinder. Okay, actually the cylinder I consider it solid. So it's basically the surface that we are talking about is on the plane flat, but inside. So this, suppose that you replace this symbol less than or equal for this symbol equal, and you specification that's inside. Inside the cylinder and on the plane XY. So normally I try to do my best to do the surface. The surface is on the plane, I suppose here, but inside this. And I try to do my best. Okay, as you know, it's like an ellipse. No ellipse, but ellipse is only the curve. Ellipse, when you talk about ellipse is the curve, one dimension. No, a surface, but the border of the surface is elliptical. It's over, right? Actually, what's the name of this surface? Well, the name is this. This is this. What kind of this? Elliptical this. Elliptical this. And the first name is this. The last name is elliptical. Entonces, what is the parametrization of this? The parametrization, well, no, the parametrization is easy because, for example, you define the vector value function, two parameters, because it's surface, two parameters. And the parameter that I put the name is R and theta. Because theta, I suppose, is a parameter that go from 0 to pi, because it's completely full circle for this, sorry. Entonces es R cosine theta, pero R is a variable, okay? Because R, I suppose, is the radio, and the radio cover everything from 0 to one specific value, que is no constant, is variable. And your specification, the x component, this is the x component R cosine theta, and the y component is sine, no? Is sine. And this guy is x, this guy is y, no? And the c, is this, would be obviously 2 minus y, no? But remember, in the vector value function, your specification, the new variable is r and theta, no? It's easy. It's 2 minus y, que y is r sine theta. This is my vector value function. Now, the domain is super important. The domain is super important. The domain is theta and r. Okay, call r. Theta go from 0 to pi because I want the full elliptical disc. And r go to 0 to 1 because I know very well that my disc is bounded in the inside, no, inside the cylinder with the radius 1. Not necessarily the radius 1, you know, it's the maximum radius 1. This is my domain in the parameters r and theta, and in the GeoGebra you write surface parentheses the x component that I want to call b cosine u, comma, otherwise would be b sine u, and the c is 2 minus b sine u, comma, for example, the order is not important. U vary from 0 to pi, and B vary from 0 to 1. Okay, and when you press enter, you see our famous disk, elliptical disk. Cool. I want to show you now. Do you understand? It's a little bit. It's not obvious. You need to tell your brain for the new situation to define the surface, no? And you, so far, you don't remember very well the name, identification of the surface, and the classical X, Y, Z axis, no? Which so I want you remember. Let me see where this surface is right now. Okay, let me try. So in this case, okay, here you go. Parametric surface. Okay. Let me share the screen. Switch screen. Do you see Georgia right now? Oh no.
Yes, we see it now.
Absolutely. Good. Okay, and the example we start today was cylinder. Look at that. You can see here. Bam! Look at that. It's a beauty, guys. Cylinder. In this case, I modification the height of the cylinder from 0 to 10. But the beauty is that you can use any height and any portion, semi-cylinder. For example, suppose I want the -10 here. Enter. Boom. Do you see? Now our cylinder is from -10 to +10. Okay. It's really amazing. Yes or no? You want 0? Well, let me restore 0. 0, 0, 0. 0, 0. And you define everything radio, high. Okay. No problema. Do you understand cylinder? Do you see more clear now? An ellipsoid. Look, ellipsoid. Que we studied. Ellipsoid. Wow. Look at that ellipsoid. Ellipsoid. Es obvio. In this case, the major axis is Z axis because the coefficient in C is 6. And the coefficient X and Y. X is 2 and Y is 3. It's ellipse. This is the XY. Remember the axis. Okay. Ellipsoid, ellipsoid, ellipsoid. And the famous example, the last example was a disc. Look, it's this. Oh, nice. A disc. But let me try to understand this disc. This disc comes from of the intersection a cylinder. Look at that. And a plane. That plane. You see that this surface is on the plane, pero not all the plane. It's a specific part that is intersecting in between cylinder and plane. Do you see the beauty of that? Let me remove the plane. Yeah. Let me remove. Okay, in conclusion, guys, we can parametrization any surface. And not necessarily the infinity surface, one specific portion of the surface. Okay? Cool. Okay. Cool. Excellent. Beauty. We are learning little by little. Okay, let me come back to the whiteboard. So in this moment, so you understand, not 100%, you understand much better the surface. We are studying new thing now. using this idea. Do you see whiteboard? Do you see? Do you see whiteboard? Okay. We study now surface integral. Okay, que is the last kind of integral we study. No more integral. Remember, in Cal 1 and Cal 2, we studied the integral, antiderivative, or defining the integral. Only one. In Cal 1 or in Cal 2. In Cal 2, we study more interpretation, more method. This is multivariate with me. Double integral. Triple integral. Okay? The double integral and the region R. The region R is flat. Maybe in the XY plane or another plane. But flat. The triple integral is a solid, T. Interpretation de doble integral es volume. Bueno, depende always the nature of the integrand function. Si the integrand function is no one, it's volume. Si the integrand function is one, it's area. And the volume and the triple integral, sorry, the interpretation is mass. Si you suppose that the integrand function represents density or another thing. Entonces now, si the integrand function is one, entonces volume, no? We study also the line integral. Line integral represents the mass of the one wire, one cable. It doesn't matter if it's curve B, you parametrization this curve, and when you multiply it by the integrand function that represents the density, linear density of the mass, you compute the mass. In the particular scenario, que the density is 1, entonces is the R length. Making sense, right? Now we study the last one, que is surface integral. What is the difference between this and this? The difference is that region is flat in the specific XY or XZ or YZ plane, and this no, this is curve B. This is surface curve B. Entonces, what is the interpretation? Well, it's the same interpretation. When you compute this surface integral, see the integrand function here is no one. E represents the density of the mass, pero in the superficie, in the area, surface density. Okay, it's maybe kilogram per meter square. And this is ds. Okay, it's important the notation in the line integral we use other ds. But this I put lowercase and this is capital because it's elementary infinitesimal r length and this is infinitesimal surface area. Okay, so now the multiplication any integrand function ds give me the mass, but the mass of the one object is 2 dimension and it's curve B. Okay. Now, if the integrand function is 1, entonces you give me the surface area. But not the surface area that we compute in calculus 2. Because in calculus 2, you compute only surface area formula for the solid of revolution. And this is particular. Now will be able to compute the surface area for any surface using the new idea for the surface integral. Boom. Okay. I promise, see we have time in the course, I try to explain in detail again the different kind of the integral. I summarize again the different kind of integral we have. we studied throughout the course, and the connection in between them. Okay, so suppose that the idea is clear. The idea is we have surface. Okay, we have surface. This is our three-dimensional space. This is our three-dimensional space, X, Y, Z. And with this surface, no solid, surface. It's the peel. Okay, and as always, we chop this in infinitesimal ds. Infinitesimal ds. Capital. ds is area. Now, well, so we are doing the Riemann zone. So we have a Riemann zone. That the definition of this new integral, surface integral, is you take the function g. The function g, who is g? G is the density. So I suppose the density of this, que no necessarily is constant, it's a variable, que depending of x, y, and z, and you multiplication by ds, que ds is infinitesimal, no? Area, entonces the symbolic way, similar to the line integral, you put line integral on the curve C, you apply surface integral on the surface S, que es completed curvy, ¿no? En general. Entonces es el Riemann zone. Es el Riemann zone, o sea, doble summation, because it's two dimension, of the multiplication G, que es the density function, integral function in general, in any point. Suppose I pick arbitrary point here. So I call arbitrary like x after, you know, you are familiar with this. Y after and z after. A multiplication by delta, capital S. And you approach the limit when the delta S approaches to 0. Of course, here, not too much specification. I put it different pieces, and that's it. Pieces. Okay. This is the idea. It's important. Well, how we compute that? This is very, very complicated. I want to explain three different ways to compute the surface integral. But you don't worry for this, so don't be scared, because there are too many formulas. No problem, guys, because there are three different ways to compute the surface integral. And in the test, no, in the test you decide the way you consider better. What is the advantage and disadvantage? Well, the problem is that there are some way in which is too long, or the integral that is coming is very, very complicated. Okay, another is easier, depending, no? Depending. I want to explain the three ways. Okay. But important to say something more this in the definition. If the function g, x, y, z is equal 1, the answer of the surface integral is surface area. Okay, and you declare it like that. The surface integral 1 ds is equal surface area. Cool. So the interpretation is clear. So definition, interpretation. Now, how we compute that is the challenge. Clear so far?
Yes, it's clear.
One fantastic way is using parametrization. Because we studied before parametrization surface. Entonces, what is the idea? The idea is, suppose that we have our surface Let me try to do one portion of the surface. This is surface. And the action of the parametrization. You are doing the parametrization, this surface, like that. Vector value function, u comma b, is equal, is a vector. And we have the x component as a function u comma b. I call x. Que es like the name of the function, pero es double meaning because it's a function. So instead you put, for example, f of x or g of x, I put x because I want to emphasize that this is the x component, no? And y as a function u comma b, and z as a function u comma b. Okay. So now when you are doing the parametrization, somehow you stay the connection one-to-one to any point here, to any point in the new plane, que es the UV plane. Because you are doing well, the parametrization is the optimal. So now our domain is a rectangle. You see before, I try to set parametrization, there are infinity ways to do that. Therefore, not always good. Okay, entonces, what is the good? What is the optimal? Well, the optimal is when the new domain in the UV plane is rectangle. Okay, now this, for example, this element in the area, this is ds. Okay, in this case is considered like a vector. You, for example, here this element, suppose que es this element, and it is, but it's easy to compute the area in this plane than this because it's a curve B, not good. Entonces now, similar to the idea that we use in Jacobian, you, for example, you differentiate the vector value function with respect to U, and you differentiate the vector value function with respect to B, and you are doing the cross product. But remember, cross product, so interpretation cross product is area. Actually, it's not like that. It's RU, DU, cross product, RB, DB. And this give me DS. So DS is actually, it's the actual value because DS is a scalar, no vector. RU cross RB, and the UDB no vector es scalar, entonces es DUDB. Wow, it's a formula. It's a formula que state the connection in between this area que es curve B and this area que es no curve B, a flat, and also it's super easy because it's rectangular. Okay. Entonces now, what is the formula que we using to convert somehow the surface integral? Suppose que I need to compute surface integral and the function g x, y, z ds and one double integral in the region R. Who is the region R? This is the region R. Who is the region S? This is the region S. It's curve B on the surface. Well, to say you copy that, copy the integrand function g, and you plugging in, this is one symbolic way, guy. You plugging in the vector value function like that. Inside this. That means that the vector value function have x component, y component, and z component. Basically, the thing we are doing is replace this x, this y, and this z by the corresponding function here. Symbolic way, I just plugging in vector value function inside the g function, que is the integrand function of the surface integral. And what about ds? Ds is the formula. The formula is a magnitude, the cross product, this and this, du dv. And you set out the limit, the rest is piece okay for us. This is double integral. And this is no, this is surface. Integral. The limit, well, in this case, si es rectangle, es piece okay. We integration in this direction, for example, in the direction B, from this to this, A to B, and after you open the window from C to D. Super easy. I promise, can you see example of this? Okay? But you understand the basic idea? So finally, exactly the same happened in the line integral. When you compute the line integral, you ending in single integral like Cal1 with the parametrization, and surface integral is exactly the same idea. You parametrization the surface and you apply this formula. Okay, actually it's the parametrization of the surface. This is one approach. Another approach, que is the most common approach, que you see in the books, because the books don't explain very well this, is the explicit. Explicit, this is the name for. What mean that? What mean explicit form? Well, suppose that you have, for example, a surface equal f comma x comma y. Suppose we have surface. Suppose we have, for example, ellipsoid. Or suppose you have no ellipsoid, que es more complicated, sino es paraboloid. You see? Que es expressed in explicit. Explicit in mathematics means when you isolate, in this case, the dependent variable c. This is explicit, no? Remember in single variable, y equal f of x is explicit form. However, f in x comma y is equal 0 is implicit. Implicit, no now, after. Explicit. Therefore, the idea behind this idea, the explicit form, is, well, again, parametrization, pero parametrization not exactly the best way, no. Sino using the graphic part. The graphic part. This is the graphic part. Entonces, this parameterization, you suppose, remember, the surface, we need two parameters. You suppose that x is x and y is y. And what about z? Well, z is f x comma y. I call this is explicit form, I call like a natural parameterization. But this is my name, okay, my mind working perfectly. Okay, so now we're using the formula that we studied before. Why not? You compute, for example, you define a vector value function using two parameters, okay, the no ub. No, I don't like ub, I like xy. Advantage and disadvantage, okay? In this case is, bueno, is x, y is a parameter, and c is f of x. This is the same idea. Look at the vector value function and parametrization is the same. The idea behind this is that in the parametrization equation, you copy 1, 2, 3 equation, and the vector value function, you condensing this in one vector, que is the position vector, no? Que describe, in this case, surface, because we have two parameters, que is x and y. C no, C depends somehow of the x and y. So you compute, for example, the partial derivative with respect to x. Similar idea that we are doing this. In this case, we are doing exactly the same, but in this case, we're using UB. UV is like a generical. It open the door to another coordinate, for example, cylindrical, spherical. This is no, it's a rectangular XY, classical. Well, you differentiate this, and the derivative is vector value function with respect to x, derivative x with respect to x is 1, derivative y with respect to x is 0, and derivative this function with respect to y is partial derivative f with respect to x. Do you follow me? Do you follow me? Likewise, partial derivative of the vector value function is 0, is 1, and it's a partial derivative with respect to y. Okay, bueno, let's do in cross product. Because remember, cross product is somehow related with the area. So you are doing the cross product is determinant, no? IJK, you copy the first vector gets 1, 0, partial derivative function with respect to x, 0, 1, partial derivative function with respect to y. And give me a vectors. And this vector is minus fx, comma, minus fy, comma 1. If you want to compute the magnitude of this vector, exactly like the equation we studied before, magnitude is equal to square root, square each component is fx squared, because negative doesn't matter, because when you square become positive, fy squared plus 1 squared is 1. Okay, so now in this point of view, we can compute the famous ds like this square root fx squared plus fy squared plus 1, and you put here dx dy. Actually, you convert the surface integral. Let's copy that. Let's copy that. You copy the famous ugly surface integral, where the integrand function is g, this is ds, and double integral. And this double integral, well, you plug in here the vector value function, que is equivalent in this specific case, que you replace x for x, and you replace y for y, but you replace z like f x comma y. Okay, now what about ds? Well, ds is this. ds is square root fx squared plus fy a squared plus 1 inside the square root everything dA. Now who is dA? Well, in this case is dx dy or dy dx, the way you prefer to integration, no? Or in general dA, because maybe according to the specific surface, maybe we ending in polar or no. So now this idea that I did in this example is valid if the graph, so the function or the equation gets given is this. Suppose the majority of the example is this guy. Suppose, but in general, I want to discuss. Suppose que no, you have explicit, but in explicit you have different idea. You have, for example, isolate y as a function of x, c, or x like a function, let me call p, y, c. Entonces the formulas es similar, except que the surface integral, que I don't want to copy again, is equal to the double integral in the region R. You copy g, is x, comma, y is h, x comma c and CSC. And the S is square root partial derivative of the function que represent the surface is with respect to x squared plus partial derivative with respect to c squared plus 1. And this is the A. And the A in this case is dx dz or dc dx, depending on the direction that you want to integration. And this case is similar. In the region R, the region R lie on the plane x z plane. In this case, the region R lie on the y c plane, que es the plane que contain the independent variable in that case. Entonces G, entonces es x es P, y, c, y, c, and the ds part, this is the ds part, no? Is square root px, pues a partial derivative p with respect to x, with respect to y, sorry, because we're using to compute the independent variable, and p with respect to c squared plus 1 dA, and dA in this case is dy dc or dc dy. All right, dc doesn't matter. Okay, in conclusion, you don't worry too much for this equation because the majority of the scenario, the graph is given, but it's possible. Is the equation for the surface is, well, maybe it's given not necessarily in explicit. It's given in implicit or in any way, and you write an explicit when you automatically isolate z, for example, or isolate one variable. Or isolate one variable. Do you follow me? Do you understand the idea? I promise que you see example. I don't know si today or not. I suppose yes. At least one example. And that's it. No. Let me explain now the third way. So far, to compute surface integral, we study parametrization, completely general parametrization, UB, que not necessarily always is UB, maybe it's R, theta, phi, depending the symmetry of the surface. Si es spherical, it's obvious que we're using a spherical coordinate. It's the easy way. Si es cilíndrica, it's obvious que we're using cylindrical coordinate, and so on. But sometimes, so the third approach to compute the surface integral is implicit form. Okay, implicit form. Let me explain the idea behind this. Explicit, you know very well. Explicit is, for example, C is equal f in x comma y. Suppose I want to express it in implicit. Well, you move C to the other side, either way, and you copy like that. F of x comma y minus C equals 0. And you call this guy like a capital F. X comma y comma C equal to 0. And this is the implicit. So the implicit is you start at the beginning under the supposition que my surface, no integrand function, surface, is expressed in implicit. There are many examples, no? Sphere, well, any surface you know, you can write the equation for the surface in implicit. Entonces you know very well in the chapter 2 que to find the normal vector, we can compute the gradient. Gradient of this. Who is gradient? Is capital F. Partial derivative capital F with respect to x. Partial derivative capital F with respect to y. Partial derivative capital F with respect to z. And this is the gradient, by the way, the gradient is a normal vector to the any surface. Normal vector. Normal. It's a fantastic way to find normal vector. Suppose I want to compute this gradient, is a normal vector. This is a normal vector. No uninormal vector, it's a normal vector. It's perpendicular to the surface because under the consideration that the gradient is always perpendicular to the surface level. So now, if you perform the dot product in between this and this vector, therefore is fx, fy, fc, dot product, and the k vector is 0, 0, 1. Es obvio que es fc. So the only guy que stay alive is this. The only multiplied by 0 is 0. Okay, therefore, if you take the gradient again and divide it by magnitude, or no magnitude because actually it's a scalar, but normally in the book it's called like that. Well, magnitude of f, dot product k. Let's see what happened. Magnitude is. Magnitude is square root fx squared plus fy squared plus fc squared divided by square divided by fc. In this particular example, this fc you put inside the square root. You have fx divided by fc squared plus fy divided by fc squared plus fc squared divided by fc squared 1. And then I suppose that you remember in the chapter 2 implicit differentiation, and you suppose that formula to compute, for example, partial derivative f with respect to x is minus partial derivative x, pero implicit divided by partial derivative z. I suppose you remember that formula in the chapter 1, chapter 2, when you study implicit differentiation. Well, this is half minus, but it doesn't matter because when you square it, they disappear. So now this is equivalent. I prove mathematically that this is equivalent to say fx squared plus fy squared plus 1. Whoosh. And this looks like similar to the formula for ds in the explicit form. What is the fantastic conclusion then? Well, we can compute it not in this way, sino in this way. So ds, using the idea behind the implicit is the magnitude gradient of the equation expressed in implicit divided by magnitude of the gradient multiplication by k vector, and this is dx dy. Likewise, well, okay. So now what should I do now in the surface integral? On the surface integral, you compute the surface integral ending in double integral in the region R. The integral function is x, y, z. And the famous ds is this. You copy this. In this case, dx dy. And this is the only way? No, of course no. You can, for example, compute the double integral, the surface integral, like a double integral, in which you copy again the integral function. But another possibility is the gradient. And you, for example, here the gradient dot product, J. And when the situation happens, this dA is dx dc, or dc dx. And another possibility is, again, the integral function. Magnitude gradient divided by magnitude gradient dot product k Okay, no, I. Entonces, when the situation happens, you projecting on the YC plane, dy dc or dc dy. It's obvious that the most popular equation is this. Okay, but it's not important. It's in general. Entonces, too much formula. Of course, you don't need to memorize this because you copy and you have in your notebook, no? Let me see a couple. Yeah, a couple. No, 3 examples I bring today. 3 examples of the surface integral. We convert the surface integral in double integral. Okay. No more theoretical part. Example 1. Example 1. Suppose que I need to compute surface area. Of one surface que es given like that, no? C plus x squared plus y squared equal 1. Above xy plane. Okay, it's equivalent to say, no? C greater than or equal to 0. Okay, let me try to understand this area, this surface. Well, this surface is, if you suppose que, for example, you write an explicit form. Well, you isolate the z. C is equal 1 minus x squared minus y squared, something like that, right? So let me try to do my best. My best is, this is 3-dimensional space. Okay. No, the negative part of the C is illegal. What kind of surface it is? What kind? Identification this. First name, last name, along, what axis? It's going up, it's going down. What is that? Name. We finish calculus 3, you never learn identification surface. Oh, solid. No, surface. No, nobody remember. David, Alvaro, Teo is leaving. No, Teo is here. Daniel? No? Okay. No variable missing. C, x, and y. But x and y is a square and c no square. On the right hand side is no 0, is 1. In the original equation. Go ahead.
Elliptic from?
Elliptic paraboloid. Yeah, you are right. Actually, it's circular. Because the coefficient in x and y is the same. O sea, ese es círculo. ¿Eh? Circular paraboloid. Paraboloid. Now, is paraboloid open up or open down?
Up.
Oh, no, down, because it's negative. What is the what is the intercept on the z-axis? What is the intercept with the z-axis? Here. What is the intercept with the z-axis? You declare x0, y0. A1, no? And this parabola, guys, look, it is super easy. Suppose que I am doing traces. Entonces, ahí declaré y0. Entonces, C equal, I don't want to teach you this again. Entonces, si you're doing in the plane, que es the plane XC, ese parábola. The Z intersect 1 and the parabola up and down because it's negative, it's vertical parabola. Like Y happened here, but in X and Y. Entonces, ese circle, UE, ese circle, no, not good. Ese circle, let me know, okay, ese circle, and this is the parabola. No, very good, pero it's okay, I try to see. This is my surface. ¿Es clear o no? Ajá, entonces si C es 1, si C es 0, sorry. Si C es 0, si C, I analyze C 0, the equation is reduced like that. X squared plus y squared equal 1, que es a circle with the radius 1, que actually is this. This point is 1, this point is 1, everything is 1. And this is 1. ¿Es clear o no? ¿More clear o no? O sea, the way, o sea, we need to identification surface, we need memorize the formulas. But to complement this idea, you are doing intersecting traces. Exactly what you studied in the chapter 1. Okay. Now. The idea behind is que in this example, they want surface area. And surface area indicate us que the integrand function is equal. Now, the thing I try to compute is the area que I highlight in blue color here, cyan color, is this area que es curvy, ¿no? Es curvy, right? Entonces, in my paper, I am doing first in implicit. I don't know why. In implicit form. Basically, sorry, I forgot to say that the most important is that the surface integral that I want to compute now is surface integral, and the surface S is this. Yes. Because the integrand function is 1. Because I want to find surface area. Cool? The challenge is, who is DS? So, there are 3 different ways I using implicit form. And the implicit form, the first thing you should do is write the equation in implicit. Okay. Implicit is, okay, implicit is like that. Fx, comma y, comma z equals 0. So you're right. X squared plus y squared minus c minus 1 equals 0. Okay, the original. Okay, and you find the gradient. The gradient is a vector, partial derivative. This guy will respect the x, 2x. Partial derivative will respect the y, 2y. Partial derivative will respect the z. Es minus or plus. No es plus. Here es plus. Es 1. Boom. Do you see? Magnitude this. Square root 4x squared plus 4y squared plus 1. Now, if you compute the dot product with the vector k, because I pretending projecting onto the XY plane. So I convert the surface integral to the double integral in the XY plane, the region R is XY plane. You perform the dot product between the gradient dot product K, que es 0,0,1. Es obvio que es 1. Therefore, the ratio between, so according to the formula say que ds is equal magnitude gradient divided by magnitude gradient dot product K. And this is dx dy, no? In this case, the bottom part is 1, and the top part is this. So basically, our ds is square root 4x squared plus 4y squared plus 1 dA. And dA, I know que es dx dy or dy dx according to the best way we need to do. Okay, or bola. Okay, entonces, we finish? Of course, no, we don't. We finish when you have a numerical value, okay, the area, the surface area of this. Okay, entonces now, I set up the double integral. I know that the integral function is 1, cool. So we have only ds. ds is square root 4x squared plus 4y squared plus 1 dx dy. And what about the region R? Who is the region R? Region R is the projection. This is the problem in 3D. Now we see the problem in 2D. 2D is obvious que es a circle with the radius 1. This is my region R. This is my region R. Right? My region R, this region R is this. Therefore, the best way to compute this double integral is polar. It's obvious, right? And you chain to polar. And chain to polar is too easy because you factor out 4 here, we have x squared, and x plus y squared is r squared. So my integral function is 4r squared plus 1. And don't forget que dx dy, the Jacobian in polar is r dr dt. And the limit is obvious, is from 0 to 1, is the radius of this region, and from 0 to 1. Okay? And this is not super complicated, but it's doable. You can separate, and you apply substitution. The answer is 5 radical 5 minus 1 over 6 pi. It's the answer. Okay? I want a professor. What is the reason you make a decision to do in implicit? No, I want to do in 3-way. I don't know if we have time today or no. But do you understand the idea? It's a formula, guys. It's a formula. So in this case, in this problem, when I need to compute surface area. Immediately, I know that the integral function is 1. No density, no. I need to find the surface area of the one piece of paraboloid. Now, immediately I compute the famous ds using the formula for the implicit, and that's it. Suppose that I want to, another student say, no, I don't like this. I never understand very well this. Let's do it in explicit. I don't want that you are doing conclusion now. Okay, what is the best way? No. Depending the problem, it's best implicit, explicit, or parametrization. Suppose explicit. Well, explicit is you isolate the C, for example. This is my surface. Okay, by the way, this is f of x. This is the identification, clear que es explicit. Okay, and the formula for the explicit say ds is equal to square root, but this is square root partial the f with respect to x squared plus partial the f with respect to y squared plus 1 dA. Be careful, because this f is not the same of this f in implicit. So I guess in this case in implicit, this is capital F, capital Y, and capital C. In this case, no. In this format, we have no capital F's with respect to C, and you have little lowercase f, que es the formula for the explicit. Entonces, the formula is super easy. Look, partial derivative this with respect to x is 2x squared plus partial derivative y is 2y squared plus 1. And obviously dA is dx dy or dy dx. Actually, my formula is ds is equal 4x squared plus 4y squared plus 1 dx dy. And you get exactly the same conclusion. The rest of the problem is the same. Do you see? They are super fantastic connection between this formula. Curiosity. In the rescue time, que es 10 minutes, so less than 10. We are doing this problem with the parameterization. So the parameterization, suppose that you never remember the equation for the conic. The conic, no, the quadratic surface. You never remember paraboloid, you never, so how you remember parameterization is more complicated. The parameterization, let me try. Now parameterization. Suppose that I don't like explicit or implicit. No. I focus on parameterization. I want to parameterization this. It's our famous paraboloid, no? And you define a vector value function. In this case, look. I can, using my imagination a little bit. Guys, you need a little bit imagination, right? Suppose that x is equal r cosine theta. Y is equal r sine theta. This is the classical formulas for the polar. And C is this equation. So this equation is 1 minus r squared. Make sense? Make sense? Entonces you have a vector value function que depending of two parameters, que es r and theta, no u and b, or u and b, whatever you want to call it. The name is not important. Okay, the first component is r cosine theta. The second component is r sine theta. And the third component is the z component is 1 minus r squared. Boom. Okay, that's it. No. You need a specification. Domain. Domain is theta and r. Theta go from 0 to pi because it's a full circular paraboloid, and r go from 0 to 1. And this is our domain in which you finish the double integral to convert surface integral to double integral. To find the s is a little bit more complicated, but no big deal. You differentiate r vector value function with respect to r, okay, the radius, it's coincident, the same letter, and you differentiate with respect to r. The answer is cosine theta, comma, sine theta. So you consider theta constant, no? And this is minus 2r. Derivative this with respect to r is minus 2r. And you differentiate with respect to theta. Is minus r sine theta, comma r cosine theta. So I am doing the derivative with respect to theta, and this do not depending of theta, this is the derivative is 0. And you perform a cross product in between this derivative I, j, k, and you copy cosine, look, cosine theta sine theta minus 2r pull, and you copy minus r sine theta, r cosine theta, and 0. And when you are doing this, you know how, the answer is minus 2r squared cosine theta, comma, minus 2r squared sine theta, comma, r. Okay, if you want to find the magnitude of this cross product, is square root of this guy squared gets 4 r to the 4 power cosine squared theta plus 4 positive again, no? R to the 4 power sine theta squared plus r squared. So you factorization r squared and manipulate some algebra, and you manipulate, and when you seek a sine squared and cosine squared together is 1. The answer is this: r square root 4r squared plus 1. Therefore, this and this parameterization que I did that is square root r 4r squared plus 1 dr d theta, que is our new variable in the parameterization. No? Now, if you are doing now the surface integral que they want que you are doing to compute the surface area, you convert in double integral, the integral function is 1, you copy here the parameterization, the ds, is r square root 4r squared plus 1 dr d theta, and this is a double integral, but no double integral, and you don't need, this is the magic of this, you don't need polar now. We are talking about r and theta, however, our region is rectangular. So no Jacobian, the Jacobian is somehow implicit in this idea. So r go, r, suppose que I integrate first with respect to r from 0 to 1. And theta go from 0 to pi. Boom. Guys, and we get the same answer. Okay? We get the same answer. Okay? This is look like science fiction. Look like science fiction. I promise in the last lecture I want to integrate everything conceptually, no? This is one of what is the reason that we have no Jacobian? You change variable or you don't change variable? No, you are doing parameterization. It's different parameterization to change variable? A little bit. Okay? Okay, guys, then we continue. You okay? Thank you. 3 different ways. Of course, in the test, when the homework and whatever, you are doing in only one way. The way you prefer. The way, even some book using only one way. Not 3 way. Okay, guys, we finish. Bye-bye. Have a nice day.
Have a nice day, Professor.
Take care.